Hi, so welcome to another video. This is a follow-up on the Electro-Voice amplifiers. If you saw my review, I said one was overheating and I showed you one was blown up in this switch mode power supply circuit. So let me give you a look. I'll zoom in a bit. This is as close as I can get with this current camera today. So this switch mode power supply down here, I said it was I figured it was an oscillator circuit, but there's a couple of diodes, FET, a transistor, and other diodes, resistors. I'll put a picture on the screen to show you what value these components are. So the main FET was blown up. I've taken it out, replaced some resistors. There was 100 ohm, 150 ohm, 100 ohm up here, and that was about it, I think. Measured the capacitors, they seem okay. If you've seen my Mackie 450 repairs, you'll need to know these capacitors need to be correct. Otherwise it won't oscillate at the right frequency and it will just blow up. Now you don't have to, but I took out the transformer just to make it easier so I could see what I was doing. So as before I said, this is the mains filter. These are common mode chokes, a couple of capacitors, bridge rectifier, so we are rectifying the mains, so we'll get 320 volts roughly in the UK. This large polypropylene capacitor is connected to the transformer, the primary. So this primary is AC coupled, which is good. This is a UC3845 pulse width modulation controller that simply drives that FET. Now there must be a feedback network from the power supply over here. There's some components and then an optocoupler here. So long as this is okay and not blown, we'll be good to go. Where the mains comes in, there's some high value resistors, large wattage. So one or two of those will be dropping the power down to something like 15 volts to run this chip. This chip actually cuts in around about 9 or 10 volts. So I put 10 volts on it today. Positive, ground and a scope. Let me give you a look at the waveform. Well, so there's the power supply, so at 10 volts running to that FET driver at 10 milliamps. And there is the output from that FET driver going to the gate of that FET that I haven't put in yet. So if one of those capacitors were faulty, you'd see this maybe running like over 100 kilohertz, which would be wrong. And if one of them had failed, you might have jitter, and this would be fluctuating a lot, which you can't afford to have. So there's our peak to peak, 13 volts, 46 kilohertz, which is fairly rock steady. So that's our result with 10 volts and no load. Probably change once the transformer goes in and the feedback network starts working. So that's what you're expecting, something like that. So let me explain the brief primary circuit of this transformer and FET. Did a quick sketch. It'll probably be hard to see in this light, but I couldn't find my biro, had to use this gold pen I had. So we've got 320 volts DC in Europe and UK. Primary of the transformer, that's our FET. That will probably have effectively a diode across the source and drain, stop it blowing up. It's not actually a diode, it's just the way the diode works. That's the gate, that's the source. Now we would ordinarily have a sort of 2 or 3 watt 0.1 ohm resistor, but to save on the manufacturing costs, maybe, I don't know, they've used 9 1 ohm resistors. So 9 in parallel gives us 0.111 ohms. So on the gate drive is driven from the chip by 150 ohm to the gate, and then to discharge it we've got a high-speed diode and another 100 ohm resistor. These were actually both blown up, but the diode was okay. The FET was short circuit. That's the basics of this circuit. So that 0.1 ohm resistor is done with these 9 1 ohm resistors. So remembering resistors in parallel. So the resistance total is, so 1 over R1 plus 1 over R2 plus 1 over R3, etc., etc. So we have effectively got 1 over 9, because we've got 9 1 ohm resistors. So 1 divided by 9 equals 0.1111. Resistors in parallel. So I initially thought this was to save cost on like a pick and place. You just have the pick and place machine, pick up a load of resistors, stick them in. But then I thought, no, we've got big resistors here that have to be put in by people, so don't really understand that. And if you saw my other video, you see the tracks are destroyed, so this hasn't worked, has it? So I've got a 0.1 ohm resistor, and I've sat it on the legs, I've sat it on the pads, bent it out of the way, because if it explodes, you don't want it destroying the components underneath. Little tip. Let me show you the values of these components. So this is a picture I took the other day, put it onto a computer, used paint. So this is our FET down here, 150 ohm, 100 ohm. Hopefully you can see my pen. This is a decoupling capacitor, so probably 0.1 microfarad. This is a diode, was it Ka2, whatever that is, another Ka2 up there. This 100 ohm, so O1A, that's the code for 100 ohm. That was blown, blown, blown. Everything else seemed okay from memory. 181 ohm. And you see I've got a note over there. I tested this component. I was getting no reading between this pin and the other two, but I was getting half a volt across these two. So I think that's a FET, and it's marked 702. And you can see I've got a note, possibly a 2N7002. Now I'm not sure why they would use a FET there. I don't know if it's a switch, but looks like it's a FET and it's not blown. Have a look down there, there's the value of all the resistors here. And I've taken these capacitors off. You see C51, 2.3 nanofarad approximately, C85, 100 nanofarad, and that one's probably 100 nanofarad as well, just decoupling. Power is, ground is pin 5 and power is pin 7. So if you've got a trashed board and you can't read the identification, have a pause the video, have a look at this, and that's the values. So these gate resistors, quite a high value, 150 ohm to the gate to turn it on, and 100 ohm in line with the diode to turn it off. So if you've seen my video on gate resistors, I'm assuming there must be quite a high total capacitance in the FET and this circuit, so we've got high values to stop gate loop ringing. And obviously this 100 ohm in line with the diode, they don't want to switch the FET off too quickly. That 100 ohm is going to slow down the discharge. So it looks like it's turning off slightly faster than it's turning on. And as I say, high value resistors stop gate loop ringing. So all it leaves me to do is put the FET in, a transformer, and put it onto the mains. You saw the waveform is turning on and off, so there shouldn't be any danger connecting 240 volts. Right, so I still had this other amplifier where it was overheating. Before I forget, this 420 watt base chip needs a heatsink, and there's a little raised pad on the forming of this metal. Trouble is that pad and there's about a 2 or 3 mil gap, So there must be a 2 or 3 mil thermal pad to conduct the heat away from this to this heatsink. Now the guy who bought this, Ross, wasn't to know. I assume he's got a spare thermal pad, so I've told him to send it up. The instructions didn't tell the buyer, the purchaser, make sure that thermal pad's fitted. Now this was overheating, and the smart display, it is a smart display, comes up thermal within 5 minutes, just like Ross said. I looked, it was getting hot here, there's no temperature sensor, so I figured this chip has to have its internal temperature sensor, and between one pin and a mode, it does give you feedback. If it's overheating, it lets you know. Something like 145 degrees C. If it gets too hot, it cuts out every 100 milliseconds. And yeah, if it carries on cooking itself, it will just shut down until it's cooled back down. No idea what all these resistors here do. Not looked, don't know what value they are. But yeah, so that's the 420 watt base chip. 2 or 3 millimeters separation to this. So if you're replacing a board, make sure you put that thermal pad on. So that's the one that overheats. Simple reason why that was overheating. So I've just plonked the board on. I'm not driving any power through it yet, so no heat sinks, no heatsink clips at the moment, nothing on the base. I've plugged the input board in with the microcontroller and a DSP, and we've got life. There we are. I must say this rotary encoder does feel nice and it's responsive. I do programming, so the programming is nice, and yeah, they would want to protect their software, so I'd give them that. But hiding the circuit drawing or not making it available, no, I've worked it out for myself, as I said in the first video. Anyone with an ounce of experience on a Class D amplifier or switch mode power supply will be able to figure it out. But yeah, so this does feel nice. It's a rotary encoder, and then line levels for the 2 inputs. It is nice. I can see why people like them, and because of the DSP, digital signal processing, you can get the response to how you want it, just like the thumps, and you get a really nice rich sound. So hello, is that overheating? Well, that looks like it's overheating and starting to turn off, but it's these 15 volt regulators. Well, this one, don't know if that's a minus or plus or minus. 3.3 that does those microcontrollers. Lukewarm. One of these is red hot, so let me get some clips on here. The main, actually, that's another thing before I forget, look, me messing about here. All these mains terminals, 240 volts, totally uninsulated. What, to save a few pence, no insulation? That's crap, straight away. Metal case, 240 volt terminals, no insulation. I'm surprised that complies with our laws. Let me stick some clips on these transistors and turn it on again. Yeah, so if you're messing about with one of these EV amplifiers, be careful, because you have a risk of electrocution on this PCB, but yeah, that goes without saying. But look at that, uninsulated mains, terrible. Uninsulated mains right next to a metal case. Let me give them a few pennies so they can insulate these, do a better job. So yeah, so poor show, no insulation. So I've put these clips back on. I've borrowed one from this treble chip. This treble chip should have 2, and these treble chips do get hot by themselves without any output. So I'll leave this on for a few minutes, have a coffee. I imagine one of those LM317, so plus or minus 15 volt regulators, but they're using variable voltage regulators. I imagine one of them is cooking and going into sort of thermal protection. But yeah, so this feels nice. Oh, how do I come out? Exit. Oh, that's nice. Yeah, this rotary encoder feels nice. The programming is quite smart because the LCD's responsive. Yeah, I do like it. When I tested the one that was overheating, yeah, within 5 minutes, the volume comes up here and then it come up thermal. And when you're at maximum power, it comes up limit, big white limit. So it's smart. It is smart. But yeah, not 1000 watts. 420 watts on the bass and 100 watts on the treble. I'll connect this to my scope in a few minutes. We'll give it a test. Well, I've got my scope plugged into this EV amplifier, and so this amp isn't as sensitive as the Mackie 450s, and I've always said the 450s have got a fabulous front end. 3 operational amplifiers built in such a way they're constructed like an instrument amplifier, and the input range can be from 50 volts, you can see down here, 50 millivolts right up to 5 volts. So I've got 50 millivolts going into this EV, it's down at full volume, and I've got 5 volts peak to peak coming out. So don't forget that bass chip, it's got positive half cycle and negative half cycle, so we need both waveforms, so twice the power of a normal single chip. Right, so let me turn this input up, and I'll turn the so that's at 300 millivolts now. Let me turn the amp down. I've got it running into a 4 ohm 100 watt resistor, which I used the other day to test an SRM sub, and I melted my leads. Can't believe, so I think I'm going to have to spend, I don't know, 20–30 just to get some hooks for the end of this Keysight scope lead. They're melted because this resistor got so hot. It used to be gold, now you can see it's a browny colour. The SRMs, SWAs, HDs are really powerful, remarkable subs. Anyway, so that's warm already. At 9 volts peak to peak. 9 volts peak to peak, but don't forget we've got 9 volts peak to peak on the positive half cycle and the negative. So that's our 2 outputs from that bass chip, but we're only measuring one, 9 volts peak to peak. So 9 volts peak to peak there and 9 volts peak to peak there. So double the power. Yeah, so the programming on this is second to none. It does feel nice with this rotary encoder. See, that's full volume there. So it looks like it needs a lot more than 300 millivolts. Let's turn the scope up. That's 300 at the moment. Half a volt. $800 millivolts. Well, that's 1 volt peak to peak, and we're at full volume. Mute. So obviously that's showing us our volume, our line in at 1 volt, and with that 1 volt we can get maximum power, so which is plus 10 dB. Also, you can see we're at the limit. So let me turn down that scope until that limit light goes off. There we are, so that's half a volt. So that's odd. So half a volt is our maximum to get maximum power. Now thermal. Now this is because, this bass chip is 2 or 3 millimeters away from the heatsink, and the poor little thing's cooking, probably 145 degrees C now. It's cooking and letting us know. That's why we've got a thermal. So I really should turn it down. In fact, I'll turn it off for a minute. Yeah, so if you've repaired one of these boards, don't forget the thermal pad. As I say, it's got to be 2 or 3 millimeters thick. If I had one, I could stick it in. Maybe I need to find a piece of metal or something just to bridge that gap. So this board bolts down, clamps down. It looks like there's a track on this top end, there and there, so I've got one of the nuts just to ground it. I've got the 4 ohm resistor connected to the base here, obviously treble there, some sort of screen for interference, maybe. Yeah, those are the 2 rectifiers. There was some sort of regulator set up in here, so between these resistors and these components we must be getting our roughly 15 volts to drive this PWM modulator. For this brand new board, look, that's been arcing there. Looks like it hasn't been insulated when it's first turned on. Yet this did work. That's a bit naughty, isn't it? That could kill a brand new board in a second, or less than a second. So something like 15 volts to drive the FET driver down there. There's the FET driver. Incidentally, the one I've got from Farnell is actually the wrong casing. This case is insulated on the one I've used today, and it should be a metal case, uninsulated, which can handle more power. And that's the part number 17N80C. Hope you can see that in this light. Got this from Farnell, about £3.50 odd. That's the Farnell part number there. So I said during the review, you don't need a circuit drawing to fix these. Maybe I've been lucky, I don't know, but I fixed this without a circuit drawing. So I think it's a nice amp, nice construction. They've cut down on cost, saved pennies on the insulation on this mains, because that's just bad practice. No insulation on mains connectors. But other than that, it's nice. Nice clips to clip down the components, makes it nice and quick. But then why do you want it quick? If it's going to last forever, you should never have to undo them, should you? It's quick assembly, I guess. Let me unplug this before I electrocute myself. Yes, you won't be able to see down between the board and that chip. Let me take this out. So I'll take it out in a minute. Let me show you the waveform. So as I said, with the DSP we can get a nice response on the sound, make them sound nice, no doubt about that, and this rotary encoder feels nice, and I'm sure once you're familiar it's easy to skip through the menu. I like that, it feels responsive. Yeah, nice, they've done a good job on that. Yeah, nice. The only thing that, yeah, it's just a shame they quote 1000 watts because it's not 1000 watts, it's 500 watts. Well, 420 on the bass plus 100 on the treble. So how do you exit? Reset. Bass, treble. Location. Exit. Yeah, simple enough menu to follow, considering I haven't got the manual and this is the first time I've used one. So it lets you know where the volume is. That's nice. Lets you know if it's overheating. Lets you know when you've got maximum power on the input, which is 1 volt, but gives you full power at half a volt. It's got a lot going for it, I guess. These connectors feel nice. It's all got a nice feel to it. They've just cut pennies in certain corners. Right, so that's at the lowest volume. I haven't got any filters, a filter network on the resistor to cut out all of that 400 kilohertz, but let me turn the volume up. So So we're at 0.5 volt input, 511 millivolts peak to peak from that scope. Well, that's full power, plus 10 dB. And I'm not touching it, that's compressing by itself. And in fact, I dare say it could be that base chip cutting back because it's getting too hot. Let me turn that back down a bit. You can see the amplitude just crept up a bit. So it does what it says on the tin. So 420 watts output. If I leave that volume where it is, turn the power up here. So that's 25, 27 volts peak to peak. And you can see it's cutting itself back. Oh, and then I'm at the maximum voltage, 2.5 volt in. So if I put that back to a volt, well, 1 volt, that resistor is red hot. So at 1 volt, oh there we go, that's now going into current limit. That's that base chip protecting itself. We got roughly, let's see if I can knock it back a bit. On 25, 30 volts peak to peak. So plus, so 25, 30 on one, plus 30 on the other, so 60 volts peak to peak. That's not 1000 watts. The Mackie 450, which also aren't 1000 watts, they come up to 100 volts peak to peak when cold and come back to about 90-ish when they're hot. And I think that's the compression. This must have a compression circuit in that front end with the microcontroller and DSP. It's nice. Yeah, so that's half the chip giving us our positive going signal and the other half of the chip giving us our negative going signal. If that was just a mono system, turn out we'd only just have half this power. But it's a Class D, plus or minus, we've got effectively double the power. So 420 watts instead of 210. And our thermal is beginning to come on. So that's the feedback from that chip telling us it's getting too hot, poor thing, because it's not connected to a heatsink. Mute. I'll turn it off. Turn it off. Actually, it's quite warm here. Turn it off, unplug the mains before those uninsulated terminals kill me. And that's not a joke, because that's what can happen. Get rid of this base. Let me take this board out and I'll show you what I mean about that heatsink. Right, this is that bump, the form in that heatsink I was telling you about. So that is meant to mate with this, and this is insulated, so it doesn't matter about grounding it. But a heatsink can bend on there, boom, there's our ground. But no, that's 2 or 3 mil. That's sitting 2 or 3 mil lower than that chip. Bit of a shame. So use some special thermal pad. Oh, I haven't got one that thick. Just a word of caution: if you're repairing one of these yourself, make sure you put that thermal pad on. But why didn't they just make this a couple of mil deeper? Then no pad required. But then I guess you've got the tolerances of the board, and when it's clamped down, and if that's the wrong depth, you're going to bend the board and maybe damage something. So there's a reason for everything. That looks like some rubber foot to stop the board bending there. So just now this insulated FET didn't get that hot. It started cutting out because one of these regulators started getting hot. So as I say, they're 317, so adjustable voltage regulators, but there's plus 15, minus 15 and 3.3. what I might do, put this back together, see the frequency with it running a load, and see what voltage we've got here. So to get that full power we need plus or minus 40 volts. We'll see what we've got. Right, I've connected my trusty Pico differential probe, one to the ground of that FET driver, and then the gate through a little convenient slot on the side. That's the differential probe, just to protect my scope. And you remember we had 46 kilohertz before, but quite a wide pulse. So this is on but not delivering any power. Don't want to start tempting fate and start shorting like that gate out or whatever. So this is, I mean, it's turned on and running. So we've got 47 kilohertz, but obviously that on time is just very small at the moment. A lot of ringing though, notice. Some of that might be down to my differential probe, but so that's the gate turning on and that's off. A bit of ringing there. So yeah, that's 47 kilohertz. In fact, we've only got 5-6 volts on that gate. So now what I'll do, I'll see if I'll get my meter and see if I can measure the supply over here. Well, hopefully you can see my meter from there. So if I use this earth here, I'll probe these rectifiers. That's the case, the tab, no. Carefully not to short it out. So minus 36, and that's the tab of the other one, plus 36. So plus and minus 36. And you remember the spec of this base chip, we need plus minus 41 to get maximum power. So it's not even 420 watts, but yeah, that's just splitting hairs. So roughly 420 watts, you know, a bit under. So I suppose plus or minus 35 volts isn't bad, considering this chip is plus or minus 41. Actually, that's still turned on. Yeah, so I don't know if that base chip, that plus minus 41, is at the maximum rating or that's the voltage you need to get 420 watts out. But so you're down on wattage a little bit, you know, maybe 400 watts, but so it's not running any audio at the moment. These heatsinks are warming up. I'm in one of these regulators down here. Got red hot as you saw the display started flashing on and off. So I'm not sure why the 15 volt regulators are getting so hot. Just a few op amps, you know, on this input board, so don't know. So other than this lack of insulation there, I think it's quite a good design. They don't make the circuit drawings available, but hey presto, you don't need them. I think the DSP and the rotary encoder, it feels smart, works well, it's a good programming. You know, and as I said earlier, they would want to protect their software. They wouldn't want people getting hold of that after spending weeks developing it. So yeah, that's smart. Smart display, tells you everything. Nice amp, just not 1000 watts. And looking at this newer board, on this cap for example, that is on this side. On this older one, they've now moved everything over. Not sure why. Maybe it's going to make it more reliable. Maybe cut down on that ringing somewhere, I don't know. You can see it's been revised. So maybe the later one will be more reliable and not blow up. But this didn't seem to be getting that hot. Although obviously I wasn't running it at full power. And I can't because that doesn't touch the metal case. I need some sort of thick thermal pad. Yeah, nice construction, they work, and with the DSP they sound nice, I imagine. Hopefully this video's helped. Thank you very much.